Hey everybody! Today I'd like to continue our discussion of groups by building up our stock of examples. So let's dive right in with an example of a group. We'll start with an example that we met in the first week of class, which is the set Zn. Remember, that denotes the numbers 0, 1, 2, 3, and so on, up to n minus 1. And then we'll let the binary operation star be the operation of addition modulo n. Remember that to check that this is a group, there's really 4 things we need to check. So let's talk through those briefly. The first thing to check is closure, in other words, that this operation is closed. That's the statement that if you were to take 2 elements of the set Zn and then add them modulo n, the result would be a new element of the set Zn. That's something that we discussed last week, so I'll check off that property. The second property I need to check is associativity. So remember, that's the statement that this equation holds, and that indeed is a true fact about addition of integers, and it's still true for addition of integers modulo n. Although, to be perfectly honest, I'll never ask you to prove associativity in this class, and the reason is that depending on the context and depending also on your perspective, it's either something that's really unwieldy to prove, like it would take so many different computations to check it, or in some cases it's just something that's axiomatic. Like for the integers, if you dig into how the integers and addition of integers is really defined, you'll find that associativity is one of the axioms that we assume of addition of integers. So in either case, whether it's too complicated or axiomatic, it's not something that it's really reasonable to prove. And so again, I'll never ask you to prove associativity in this class. I'll always tell you that it's something you can assume. The last 2 things are things that we actually really can check though. So the identity, remember that should be an element that if I add it modulo n to anything, I get that thing back. And that identity element is 0, so there is an identity. And then last but not least, inverses should exist. That means that if I take any element A in the set Zn, I should be able to find something that I can add to A mod n and get 0 back. And on a first pass, you might say, well, the inverse of A should be negative A, because if I add A to negative A, I will indeed get 0. You have to be a little bit careful there, because negative A, like for example, negative 2, is outside of this range 0, 1, 2 up to n minus 1, but still I can take negative 2 and I can reduce it modulo n, meaning I can add n to it if I need to put it into that range. And so that's why I've written here that the inverse of A is negative A mod n. What I mean is you take negative A, and then if you've now gotten outside of that range, you reduce mod n to put yourself back in that range. So every element does have an inverse that checks the axioms, and so Zn under the operation of addition modulo n is indeed a group. Here's another example that we met in the first week of class, although we didn't give it a notation then. I'm now going to use the notation D4 for the set of all symmetries of a square. Remember, we saw on Friday of the first week of class that there's 8 elements in that set, like I and R90 and R180 and so on. That is going to turn out to be a group where the operation star is the operation of composition. Let's check that it does indeed satisfy those 4 properties. First of all, I want to check that it's closed. That means that if I compose 2 symmetries of a square, the result is a new symmetry of the square. And one way to see that that's the case is because we made a table that shows how to take any 2 symmetries of a square and compose them to get a new symmetry of the square. So because that table exists, I can see that the composition of two symmetries is a new symmetry. Next up on the list is checking associativity, and again, as I mentioned before, that's something that you can feel free in this class to assume. It is something that technically we could check if we really wanted to, because there's only 8 elements, and so there's only so many different ways of choosing A, B, and C to check the associative property holds. But when I say there's only so many ways, there's a whole lot of them. So that's what I mean when I say that sometimes associativity is possible to prove, but just unwieldy. So I'll totally just assume it. Okay, so next up on the list is the identity. That should be an element of D4, that when I compose it with anything else, I get that thing back again. And we used the letter I to denote a symmetry that does just that. And we even called it the identity. If you'd like, you can look back at the table to convince yourself that sure enough, if I take I and I compose it with any other symmetry, I get that symmetry back again. That's what makes it the identity element. Last but not least is inverses. I should make sure that if I start from any symmetry, that I can find something to compose it with that'll give me back the identity. That's maybe not immediately obvious, but it's something that also follows from our table. By looking at the table, you can see that no matter what symmetry of a square you start with, you can always find some symmetry to compose it with to get the identity. For example, let's say you start with R90. The inverse of R90 is R270, because you can confirm by looking at the table that R90 composed with 270, or the other way, R270 composed with R90. Either way, you get the identity. Or for another example, I could ask, what's the inverse of H? So what could I compose H with to get the identity? And again, looking at the table, you can see that the answer is actually H itself. If I do H composed H, that's the identity. So I can go down the line in this way and confirm that every element has something I could compose it with to get the identity. So every element indeed has an inverse. That's my last axiom, and so D4 is indeed a group under composition. One last example, which I alluded to a little bit in the worksheet for Monday, is something that's called GLN, R. The GL stands for the general linear group. And what this means, by definition, is it's the set of all n by n matrices with real numbers as their entries, whose determinant is non-zero. This forms a group under the operation of matrix multiplication. I won't go through all the axioms in so much detail this time, but maybe one quick thing that I'll point out is that the reason I want to make this stipulation that I'm looking specifically at matrices with non-zero determinant is that you maybe remember from linear algebra, matrices with non-zero determinant are exactly the ones that have inverses. And since my last axiom of a group is that I want every element to have an inverse, I'd better put in that stipulation to make sure that those inverses really do exist. All right, so you're going to meet a whole bunch more examples and non-examples of groups on your worksheet for today. Before the end of this video, though, I want to conclude by stating one general property that all of the groups you meet will satisfy. I'll state it as a theorem. It says let G be a group and let A, B, and C be 3 elements of G. Then if you find that B star A is equal to C star A, then you can cancel the A's from both sides there and conclude that B is equal to C. And similarly, if you're in the situation where you find that A star B is equal to A star C, then you can cancel those 2 A's on the left and again conclude that B is equal to C. Because we can think of this as this cancellation process, I'll refer to this theorem as the cancellation property of groups. I'd like to prove this theorem for you because I think, for one thing, it's a good exercise in using the group axioms. So it's an if-then statement. It says, if B star A is equal to C star A, then B is equal to C. So the structure of a proof of an if-then statement like that will start by saying, let's suppose that hypothesis is true. So let's suppose that B star A is equal to C star A. And I'm now going to try to manipulate this logically using the group axioms in order to conclude that B is equal to C. The first thing I can do is use the fact that because this is a group, every element has an inverse. So in particular, A has an inverse. And then I can take these two things which are equal to each other, B star A and C star A, and multiply or star both of them by A inverse. Next, I'll use the associativity property of groups to rearrange the parentheses on both sides of that equation. At that point, I've got an A star A inverse, which by the definition of inverses is the same thing as E, the identity. And I've got another one, an A star A inverse, on the right-hand side. So there I'm using the definition of inverses. And then lastly, B star E, remembering that E is the identity, that's the same thing as B by the definition of the identity, and C star E is the same thing as C, again by the definition of the identity. So we've started by supposing B star A was equal to C star A. We concluded after some argument that B was equal to C. So that proves that first implication, that if B star A equals C star A, then B is equal to C. The second implication from that statement of the theorem has an almost identical proof, so I won't go through it here. So that's our first example of a group theory proof. Lots more like that to come, but that's enough for today, so I'll see you in class.